Infinity is a fascinating concept that has intrigued philosophers, mathematicians, and scientists for centuries. It can be used to describe something that has no end, no limit, or no boundary. It can also be used to compare different sizes of infinite sets, such as the natural numbers, the real numbers, and the power set of the natural numbers. Infinity can also be used to study the properties and behavior of functions, series, and limits in calculus. However, infinity is not a real number, and it cannot be measured or manipulated like other numbers. It is an idea, an abstraction, and a symbol. It has some paradoxes and limitations, such as the fact that adding or subtracting any finite number from infinity does not change its value, or that there are different types and levels of infinity. Infinity is a concept that challenges our intuition and imagination, and it can help us explore the mysteries of the universe and mathematics. Infinity is a very special idea that has no end, no limit, or no boundary. It can be used to describe something that is limitless, such as the size of the universe, the number of natural numbers, or the power of God. In calculus, infinity is used to study the properties and behavior of functions, series, and limits. For example, we can use infinity to evaluate the limit of a function as the input variable approaches infinity or negative infinity. This tells us the end behavior of the function, or how it behaves when the input variable gets very large or very small. For instance, the limit of 1x as x approaches infinity is 0, which means that the function 1x gets closer and closer to 0 as x gets larger and larger. 1. Evaluate the limit of the function as the input variable approaches a finite value, but the output variable approaches infinity or negative infinity. This tells us that the function has a vertical asymptote at that value, or a line that the function approaches but never touches. For instance, the limit of 1x as x approaches 0 is infinity, which means that the function 1x gets larger and larger as x gets closer and closer to 0. 1. Evaluate the limit of a function as the input variable and the output variable both approach infinity or negative infinity. This tells us the horizontal asymptote of the function, or a line that the function approaches as both variables get very large or very small. For instance, the limit of x/x as x approaches infinity is 1, which means that the function x/x gets closer and closer to 1 as x gets larger and larger. 1. Evaluate the infinite sum of a series, or the result of adding infinitely many terms. This tells us the value of the series, if it exists, or whether the series diverges, or has no finite value. For instance, the infinite sum of 1/2 and from n equals 0 to infinity is 2, which means that the series 1 plus 1/2 plus 1/4 plus 1/8 plus converges to 22. Evaluate the infinite product of a series, or the result of multiplying infinitely many terms. This tells us the value of the product, if it exists, or whether the product diverges, or has no finite value. For instance, the infinite product of 1 plus 1n, n from n equals 1 to infinity is e, which is the base of the natural logarithm and an irrational number 3. Evaluate the improper integral of a function, or the area under the curve of a function over an infinity interval. This tells us the value of the integral, if it exists, or whether the integral diverges, or has no finite value. For instance, the improper integral at 1x2 from 1 to infinity is 1, which means that the area under the curve at 1x2 from 1 to infinity is 14. These are some of the ways that infinity is used in calculus. Infinity is a concept that challenges our intuition and imagination, and it can help us explore the mysteries of mathematics and the universe. There are different types of infinities that can be distinguished by their properties and implications. Here are some of the main types of infinities that exist. Mathematical infinity. This is the concept of something that is unlimited, endless, or larger than any natural number. It is often denoted by the infinity symbol. Mathematical infinity can be used to describe the size of infinite sets, such as the natural numbers, the real numbers, or the power set of the natural numbers. It can also be used to study the properties and behavior of functions, series, and limits in calculus. However, mathematical infinity is not a real number, and it cannot be measured or manipulated like other numbers. It is an idea, an abstraction, and a symbol. Mathematical infinity has some paradoxes and limitations, such as the fact that adding or subtracting any finite number from infinity does not change its value, or that there are different types and levels of infinity. For example, the German mathematician Georg Cantor showed that there are more real numbers packed in between 0 and 1 than there are numbers in the entire range of naturals 12. He also showed that there are infinitely many different sizes of infinite sets, and that some are simply larger than others 13. He called these sizes cardinal numbers, and he used a special notation to denote them. For example, the cardinal number of the natural numbers is 0, and the cardinal number of the real numbers is 20, which is larger than 013. Physical infinity. This is the concept of something that is boundless, limitless, or without end in the physical world. It is often used to describe the size of the universe, the number of possible outcomes of a quantum event, or the duration of time. Physical infinity is based on observation, measurement, and experimentation. It is subject to the laws of physics and the limitations of technology. Physical infinity may or may not correspond to mathematical infinity, depending on the assumptions and models used. For example, some cosmologists believe that the universe is steadily infinite, meaning that it has no edge or boundary, and that it contains infinitely many galaxies, stars, and planets. Others believe that the universe is steadily finite, meaning that it has a finite size and shape, but that it is curved in such a way that it has no edge or boundary, and that it may repeat itself in a fractal pattern. Similarly, some physicists believe that time is infinite, meaning that it has no beginning or end, and that it can be divided into infinitely small intervals. Others believe that time is finite, meaning that it has a beginning, such as the Big Bang, and an end, such as the Big Crunch, and that it has a smallest possible unit, such as the Planck time. Metaphysical infinity. This is the concept of something that is transcendent, absolute, or beyond the physical world. It is often used to describe the nature of God, the soul, or the afterlife. Metaphysical infinity is based on faith, reason, and intuition. It is not subject to the laws of physics or the limitations of technology. It may or may not correspond to mathematical or physical infinity, depending on the beliefs and arguments used. For example, some religions believe that God is infinite, meaning that he is omnipotent, omniscient, omnipresent, eternal, and unchanging. Others believe that God is finite, meaning that he has some limitations, such as being bound by logic, morality, or free will. Similarly, some philosophies believe that the soul is infinite, meaning that it is immortal, indivisible, and unique. Others believe that the soul is finite, meaning that it is mortal, divisible, and multiple. A paradox of infinity is a situation or statement that involves infinity and leads to a contradiction or a counterintuitive result. There are many paradoxes of infinity, but one of the most famous ones is Hilbert's paradox of the Grand Hotel. This paradox was proposed by the German mathematician David Hilbert in 1924. It imagines a hotel with infinitely many rooms, all of which are occupied by guests. The paradox arises when new guests arrive and want to check in. It seems that the hotel is full and cannot accommodate any more guests, but surprisingly, this is not the case. The hotel manager can always find a way to make room for any number of new guests, even infinitely many, by shifting the existing guests to different rooms. For example, if one new guest arrives, the manager can ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on, moving every guest from room N to room N+1. This way, room 1 becomes vacant and the new guest can check in. Similarly, if 10 new guests arrive, the manager can ask the guest in room 1 to move to room 11, the guest in room 2 to move to room 12, and so on, moving every guest from room N to room N+10. This way, rooms 1 to 10 become vacant and the 10 new guests can check in. The paradox becomes even more striking when infinitely many new guests arrive. For example, if a bus with infinitely many passengers arrives, the manager can ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on, moving every guest from room N to room 2N. This way, all the odd-numbered rooms become vacant and the infinitely many passengers can check in. Similarly, if infinitely many buses, each with infinitely many passengers, arrive, the manager can use a clever mathematical formula to assign a room to each passenger, such that no room is left unoccupied and no two passengers are assigned to the same room. The paradox of the Grand Hotel shows that our intuition about infinity is often wrong, and that infinity can have some strange and unexpected properties. It also illustrates the difference between two types of infinity: countable and uncountable. Countable infinity is the type of infinity that can be matched one-to-one with the natural numbers, such as the number of rooms or guests in the hotel. Uncountable infinity is the type of infinity that cannot be matched one-to-one with the natural numbers, such as the number of real numbers or points on a line. It can be shown that uncountable infinity is larger than countable infinity, and that there is no way to accommodate uncountably many guests in the hotel, even if they arrive one by one. Cantor's diagonal argument. It is a mathematical proof that shows that there are different sizes of infinity, and that some infinite sets are larger than others. For example, the set of real numbers is larger than the set of natural numbers, even though both sets are infinite. The proof works by assuming that the set of real numbers is the same size as the set of natural numbers, and then showing that this leads to a contradiction. The proof uses the following steps. Suppose that the set of real numbers can be listed in the same way as the set of natural numbers, that is, there is a one-to-one correspondence between the two sets. This means that every real number can be assigned a natural number as its index, and vice versa. For example, the first real number in a list is 1, the second real number is 2, and so on. Since every real number can be written as an infinite decimal expansion, such as 3.14159, we can write the list of real numbers as a table of digits, where each row corresponds to a real number and each column corresponds to a decimal place. For example, the table might look like this: index, first digit, second digit, third digit, fourth digit, fifth digit. 1, 0, 5, 1, 0, 2, 1, 4, 1, 3, 3, 0, 8, 2, 4, 4, 0, 2, 3, 3, 5, 0, 4, 1, 0, 6, 0, 9, 9, 3, 7, 0, 0, 1, 0. Now, we construct a new real number that is not in the list by using a diagonal method. We look at the diagonal of the table, that is, the digits that correspond to the same index and decimal place. For example, the diagonal of the table above is 0.5241. We then change each digit of the diagonal to a different digit, such as adding 1 to it, except if the digit is 9, then we subtract 1 from it. For example, the new number we'd get from the table above is 0.6352. We call this number x. We claim that x is a real number that is not in the list. To prove this, we assume that x is in the list, and then show that this leads to a contradiction. If x is in the list, then it must have some index, saying this means that x is the nth real number in the list, and that it has the same digits as the nth row of the table. However, this is impossible, because by construction, x has a different nth digit than the nth row of the table. For example, in the table above, x has a 5 as its fourth digit, but the fourth row of the table has a 3 as its fourth digit. Therefore, x cannot be in the list, and we have a contradiction. We conclude that the set of real numbers cannot be listed in the same way as the set of natural numbers, and that there is no one-to-one correspondence between the two sets. This means that the set of real numbers is larger than the set of natural numbers, and that they have different sizes of infinity. This is the basic idea of Cantor's diagonal argument. It can be generalized to show that for any set, the set of all subsets of the set is larger than the original set. This is known as Cantor's theorem 1. It can also be used to show that there are some mathematical problems that cannot be solved by any algorithm or procedure. This is known as the unsuitability of certain problems. The question of whether the universe is infinite or finite is one of the most profound and challenging topics in cosmology. There is no definitive answer, as different models and theories have different implications and assumptions. However, some of the theoretical and mathematical bases of the universe being infinite are as follows. One possibility is that the universe is flat in Euclidean, meaning that it has no curvature and follows the rules of Euclidean geometry. In this case, the universe would be spatially infinite, extending in all directions without any boundary or edge. This would imply that there are infinitely many galaxies, stars, planets, and even copies of ourselves in the universe. However, this scenario would also require that the universe has a zero cosmological constant, which is a term that describes the energy density of the vacuum. The cosmological constant is related to the expansion rate of the universe, and current observations suggest that it is not zero, but positive and small. A positive cosmological constant implies that the universe is accelerating in its expansion, and that it has a positive curvature, which makes it finite but unbounded, like the surface of a sphere 1. Another possibility is that the universe is quantum and non-singular, meaning that it does not have a beginning or an end, and that it is governed by the laws of quantum mechanics. In this case, the universe would be temporally infinite, existing for an infinite amount of time. This would imply that there is no need for a Big Bang or a Big Crunch, which are scenarios that involve a singularity, a point of infinite density and temperature where the laws of physics break down. A quantum universe would avoid singularities by using a quantum gravity theory, which is a theory that unifies quantum mechanics and general relativity, the two pillars of modern physics. One example of such a theory is the quantum cosmology, which describes the universe as a network of loops and nodes that evolve according to quantum rules. Loop quantum cosmology predicts that the universe undergoes a bounce instead of a bang, and that it has a minimum size, which makes it finite but unbounded too. A third possibility is that the universe is multiverse, meaning that it is not the only one, but one of many universes that exist in a higher dimensional space. In this case, the universe would be part of an infinite collection of universes, each with different physical laws, constants, and histories. This would imply that there are infinitely many possibilities and outcomes for the evolution of the universe, and that our universe is just one of them. However, this scenario would also require that there is a mechanism that generates the multiverse, and that there is a criterion that selects our universe among the others. One example of such a mechanism is inflation, which is a period of exponential expansion that occurred in the early universe. Inflation could produce a multiverse by creating bubbles of space that separate from each other and become independent universes. One example of such a criterion is the Anthropic principle, which states that our universe must have the properties that allow the existence of observers, such as ourselves 134. These are some of the theoretical and mathematical bases of the universe being infinite, but they are not the only ones. There are many other models and theories that explore this question, and each of them has its own strengths and weaknesses. The ultimate answer may depend on the availability of new observations, experiments, and insights that can test and refine these ideas. Until then, the question remains open and fascinating.